In the video today, we'll start looking at doing some numeric modeling. We'll start out simple with an existing project that you might have seen before for the geological modeling. So this is the Marvin dataset. In this case, I'm showing just the MAR interval data with, as we can see here, has some gold values and some copper values. And the main thing that we'll look at the moment will be the copper values. So just looking at the data, you can already see a little bit of a concentration towards the top and the oxidation layer at the top. Here you see very little copper. So we'll explore some of the options for interpolating this data. But before we do that, the first step is to actually take this data and convert the intervals into point data. So for this we take the assay points, or the assay data, sorry, click on it, drag it onto our processing field, and under volumetric data we actually convert this to point data by extracting the midpoints. We'll connect the two together. Double click on this one and we'll call this mids. In this case, I'll actually add MAR because there's two drill sets in this project, just to separate the two. We don't need to specify anything else. We'll run this one quickly and show the copper values for the point data. Okay, so we can turn off the drill traces. Now, as you can see, if we increase the size, we actually have some points rather than intervals. One thing to notice is that in version 4 we also added the maximum intensity projection option, so you can actually see the higher grades directly through the lower grades. If that's something that you use in this case, in this project, it's not going to be very helpful. But if you have lots of data, it might help you to see structures more easily. But now on to the good stuff. So now we want to take this point data and convert it into an interpolated point set. So just like we've been demonstrating our modeling with, or modeling geology, we've converted our interpolation methods into functions as well. So we take the point data, and again on the volumetric modeling we have a number of interpolation options. So we have the more traditional ones, which I'll do in a minute, for an RBF or ordinary kriging. But we also introduced a machine learning algorithm, where in machine learning interpolation is called regression analysis or just regression. So we'll just demonstrate that here, and we'll open the dialog for setting the parameters. So we're looking at the copper values. We'll have copper and gold here, but we'll just focus on the copper. So we'll create a single interpolation function for the copper. We need to specify some range settings. Alright, so let's leave, well, maybe set it at 150 meters. That's sort of what we've been using for the geological model. I'll go into the smoothness and the tolerance values a little bit later. So click OK and yeah, just run it. Go to 3D tab and wait a little bit for it to process. I see that this project still had an anisotropy. So you can see the orientations dipping all the way down there. It's not really what I wanted to show just yet. I'll just reset this one. Yep, just set everything back to isotropic and we rerun it. Alright, so now we have an isotropic interpolation, and that's better. So we can go to our functions tab and we see that we have this MLCU. We have some copper cutoff grades that we can set. So here, because it's a function, we can evaluate the function on the fly at different cutoff levels. So you can play with it and see what a shell would look like for that function. So just to remember and reiterate, you're not actually seeing a shell here. This is not a triangulated surface. It's just the way we visualize it, which is using ray tracing techniques to actually demonstrate what a shell would look like when we actually evaluate it on a real grid. So below the setting, so if you click on your interpolation function, there's also a resolution setting. I'll do that in just a second, because it just produces a better resolution representation in our 3D view. So as you can see, it's a rather coarse model, rather smooth, so you can actually change some of the parameters going back. And just go back to this function here, and that's where these two values come into play. So increasing the smoothness values actually creates a more accurate model. So it's sort of reversed maybe from what you might expect. The tolerance is how accurate the estimation should be with regards to the value range of the original data. So here we say that everything needs to be roughly within 1% of the estimated or of the actual values, locations. So if we decrease that to say 0.1, we'll run it again. We'll get a slightly more accurate model. But as I said, you probably hardly notice the difference here because we set this resolution to rough. If you change that to intermediate, you start to see a bit more detail already here down there. See some blobs that weren't there before. If we increase the fine, it takes a little bit longer to evaluate, and then the model should look even finer. Yeah, there we go. You start to see a bit more detail here as well. And in this case, because we don't have that much data, that doesn't affect it too much at this stage. The other thing you can do is to play with the parameter here, which goes hand in hand with the tolerance, really. So we can increase that to 1000, or if you want to have very rough estimations, then you might reduce that to 100 or further down to 10. As you can see, every time you rerun it, it just changes the setting and starts from scratch, more or less. So now you start to see a little bit more detail in here, where you see where it starts to exclude areas a little bit more than before. Also notice that the rotation will be a little bit slower if you use a fine resolution. Just going back to the rough setting here, we'll have a quick and dirty estimation or an idea of the shape of the great shell that we might be interested in.